Hello everybody, and welcome back to Abstract Algebra. Plan for today is we are going to finish our packet on prime versus maximal ideals by talking a little bit more about the relationship between prime ideals and maximal ideals. By the way, hope you all had a good Thanksgiving. Good Thanksgiving break. They had some time to relax a little bit. Hopefully got some time to spend time with family, in a safe way, healthy way. And hope you're all doing okay. Well, this is stressful, going back to online learning. The madness continues. We only got one more week, so stick with it. You remember, you got this. Even you step. So, got my usual upstairs this week on Monday and Wednesday, assuming you're watching this on Monday. Monday, Wednesday from 10 in the morning, 2 in the afternoon. My Tuesday morning office hour, I have to cut short. Normally I go from 10 to 11:30 on Tuesday, but we're doing some job interviews on Tuesday at 11, so for our hiring a computer science professor that I have to be there for, so this office hour is a little bit short. But I'll still have my Tuesday afternoon office hour as per usual. And as far as homework goes, only thing left in the course is the final exam, which is not ready yet, probably by the time you're watching this, but hopefully will be ready by Wednesday's class. So await further instruction, please. So, which insect is the best at math? The insect that is best at math is the accountant. Okay, so before we jump into kind of the last bit of this packet here, today's just mainly going to be spent proving this one really big theorem. I want to do a quick review of what does it mean for an ideal. Remember, an ideal is just a subring of your overall ring that absorbs multiplication. And if you take anything in the ideal times anything in the outside ring, you're still getting something in the ideal. And we said that S is a maximal ideal in R if there's no bigger ideals than S. There's no ideals containing S except for the ring itself. Meaning, if T happens to be an ideal in your ring, such that S is a subset of T and T is a subset of R, if S is maximal, it would have to be the case that T would either have to be equal to S or equal to the entire ring. There's no bigger ideal other than the entire ring that will contain everything in S, in other words. And an example of that we saw was something like this. The ideal generated by 2 and x in the ring of integer polynomials. Because there's no way to make this ideal bigger, to add anything else to this ideal, except to make that ideal the entire ring. On the other hand, we said that an ideal S is prime in the ring R if whenever you take the product of two things, A and B, in your ring and get something in the ideal, it has to be the case that at least one of these two elements, A or B, is in the ideal. So kind of as an example, if we do Z mod 5Z is, or not Z mod 5Z, let's say, 5Z in ring of integers is a prime ideal, because if you multiply two integers and get a multiple of 5, one of those two integers to start with had to have been a multiple of 5. Whereas, if we wanted to look at the ideal 6z, well, multiples of 6 in the ring of integers, this would not be a prime ideal, since 2 times 3 is an element in 6z, but 2 and 3 individually are not elements in 6z. 6z is not a prime ideal because it's possible to multiply two integers together and get a multiple of 6 when neither of the original integers was a multiple of 6. And we looked at a bunch of examples of these ideal types last time, and we kind of decided that it looked like in all the examples where S was maximal, it turned out to be prime as well, but not vice versa. And so today, I want to kind of explore that relationship a little bit more between maximal ideals and prime ideals. And in the process, we're going to come up with an alternate way to look at whether or not an ideal is maximal or prime. We're going to find some equivalent conditions to an ideal being maximal versus an ideal being prime. And that's going to come about from this theorem here. Or if we assume that R is a commutative ring, commutative meaning multiplication is commutative, with a multiplicative identity 1, and S is any ideal in the ring, then it's going to turn out to be the case that S is a prime ideal in the ring R if and only if the quotient ring R mod S is an integral domain. And similarly, S is going to be a maximal ideal in our ring R if and only if R mod S is a field. Remember, an integral domain is one of those rings where if you multiply two things and get 0, one of the two things had to be 0 to start with. And a field is a commutative ring with identity where all non-zero elements have multiplicative inverses. And so by knowing properties of the quotient ring R mod S, that tells us a lot about if the original ideal S was prime and or maximal within the ring. So most of today's class is going to be about proving this theorem. Technically, we have 4 things to prove. That if S is prime, then R mod S is an integral domain. Vice versa of that. If S is maximal, then R mod S is a field, and the vice versa of that. Converse of that, I should say. So let's start proving this. So the first one I want to prove, we're going to prove part 1. Gabe, think we should go from left to right first or from right to left? Left to right? Good idea. That's what my notes have. So let's go from left to right. So we're going to start by saying, suppose S is prime. And our goal is going to be to prove R mod S has to be an integral domain. So we can show R mod S is an integral domain. We need to show that it has commutativity and a multiplicative identity. Well, it gets those things for free. So we can say then since R is commutative with a multiplicative identity 1, something we assumed, R mod S has to be commutative with identity 1 equal to, with the multiplicative identity in R mod S is just going to be the multiplicative identity in R plus S. It's the ideal where the element we're adding out in front of the ideal is just going to be the multiplicative identity from the ring R. This is going to give us the multiplicative identity in R mod S. So we get 2 of the things we need for an integral domain really quickly. We have that R mod S has to be commutative, it has to have multiplicative identity, and the other thing we need to show R mod S is an integral domain, is we need to show that if we take the product of 2 things in this ring, in this quotient ring, and get 0, one of the 2 original things had to have been 0 to start with. So let's do that. So let's suppose we have 2 elements, A plus S and B plus S, that are elements in our quotient ring, R mod S, such that the product of these 2 things is going to give us 0. What is the 0 element? The additive identity in R mod S. Well, the additive identity in this ring is going to be S, or 0 plus S if you prefer. We're keeping in mind S is the 0 element in R mod S. And then our goal is going to be to show that if the product of these 2 things is S, then one of these 2 ideals, either A plus S or B plus S, had to have also been S to start with, the 0 element. We can show that that proves R mod S is an integral domain. Well, if we are assuming A plus S times B plus S is equal to S, that allows us to say then AB plus S is equal to S. Because the product of these 2 ideals, A plus S times B plus S, by definition, is just A times B plus S. Or A times B is being taken in the ring R. So AB plus S is equal to S. So what does that tell us? That's going to tell us that AB, by definition, has to be an element in S. in order for AB plus S to just be the same as S. AB has to be an element in S. And now, here's where we can use our initial assumption that S is a prime ideal within the ring R. And since S is a prime ideal, anytime you take the product of two things in S, one of those two things had to have been in S to start with. So that tells us that either A is in S or B is in S. But if A is in S, what does that tell us about A plus S? Well, if A is in S already, A plus S has to be equal to S. And similarly, if B is in S, then B plus S had to have been equal to S. And so what we've shown is we've shown that if we take the product of two elements in R mod S, take the product of two things in here and get the zero element, S, one of those two cosets to start with had to have also been equal to S, the zero element. And thus, we can conclude R mod S is, in fact, an integral domain. Nito Burrino. So R mod S is an integral domain, if S is prime. So next, we're going to prove the reverse direction. What's that, Megan? You want to prove the forward direction of number 2 first? Get out of here. We're not doing that. Let's prove the backwards direction in number 1 before we move on to number 2 here. So in the backwards direction, we're going to suppose that R mod S is an integral domain, and then show that implies S has to be a prime ideal. So now, we'll suppose R mod S is an integral domain. And our goal is going to be to show that S is a prime ideal, meaning if we take the product of two things in the ideal S and get some, or if we take the product of two elements in the ring and get something in S, then one of the two elements had to have been in S to start with. At least one, potentially both. So we're going to suppose R mod S is an integral domain, and that A times B is an element in S for some A, B elements in the ring. And again, our goal is going to be to show either A is in S or B is in S, or both. Well, if AB is in S, then that's going to tell us that if we were to take AB plus S, we would get the same thing as S. AB is an element in our ideal S, then adding it to S just gives us back the same set of elements as the original S. But what do we know about AB plus S? That's going to be the product of two other elements in R mod S. It specifically is going to be equal to A plus S times B plus S. So we've shown that S, which you may recall is the zero element in R mod S, is equal to the product of two elements in R mod S. So now we can say, since S is the zero element in R mod S, and since R mod S is an integral domain, we've taken the product of two things in an integral domain and gotten 0. How can you take the product of two things in an integral domain and get 0? At least one of those two things had to have been 0 to start with. Then, instead of that, we'll say thus, we know that one of these two things had to have been the 0 element S to begin with. Thus, either A plus S is equal to S, or B plus S is equal to S, which is the same as saying A is an element in S, or B is an element in S. Because either A plus S or B plus S has to be the 0 element of R mod S, i.e. just the ideal S, and If A plus S equals S, then A is an element in S. If B plus S equals S, then B has to be an element in S. Either way, we've shown that anytime we take the product of two things in our ring, R, and the product AB is an S, it has to be the case that either A is an S or B is an S. And thus, we can conclude S is prime. Neato mosquito. So we've proven part one of our two-part theory. We've shown that an ideal S is prime if and only if R mod S is an integral domain. So the next thing we need to prove is the reverse direction that, or not the reverse direction, part two, which says that S is a maximal ideal if and only if R mod S is a field, meaning one of these commutative rings with the multiplicative identity where every non-zero element has to have a multiplicative identity. So let's do that. This one's going to be a little bit trickier, but we will get there. Mark my words. Elaine, don't be doubting me yet. Nick, you can doubt me if you want to because your opinion doesn't mean as much to me. Anyways, we're going to prove part two now. Prove the forward direction first. Remember, part two said R mod S is a maximal ideal in R if and only if R mod S is a field. So we're going to suppose S is maximal. As before, R mod S has multiplicative identity and is commutative. Why? Well, because we assume that R has these things, and anytime you're looking at a ring R that's commutative and has multiplicative identity, any quotient ring of R, say R mod S here, has to be commutative and has to have multiplicative identity just equal to multiplicative identity of R plus S. So right away we get two of the three things we need for a field. The only thing left is we need to show, given any non-zero element in R mod S, it has to have a multiplicative inverse. So we are going to let A plus S be an element in R mod S such that A plus S is not the zero element. It's not S. And then our goal, the last thing we need to show R mod S is a field, is we need to show that this non-zero element has some multiplicative inverse. I.e., show that we can take A plus S and multiply by something else times S and get the multiplicative identity of R plus the ideal S. Because this right here is the multiplicative identity in R mod S. If we can multiply A plus S by something and get 1 plus S, that would show A plus S has a multiplicative inverse, and we will be done. All right, let's do it. We assume that A plus S is not equal to S, because we need to assume A plus S is non-zero in the quotient ring, because if it's zero, the zero element, it's not going to have a multiplicative inverse. Which direction am I showing this one? We know that A plus S is not equal to S. So what does that tell us about A? Well, that's going to tell us A can't be an element in S. If A plus S is not equal to S, that's logically equivalent to saying A is an element in the ring R, but not in the ideal S. And now, we're going to do I'm going to define a new set of elements. I'm going to define a set of elements, S hat, that's going to be equal to the set of all things of the form AR plus S, where R is allowed to be any element in the ring R, S is allowed to be any element in the ideal S. So, in other words, I'm defining S hat to be a new set of elements. Just a set of elements in our ring that can be written in this way. Something A times something in the ring plus something in our ideal S. here's what we're going to do. We're going to show that S, which is a maximal ideal, is contained in S hat, but is not equal to S hat. Well, if S is contained in S hat, but is not equal to it, since S is a maximal ideal, meaning there's no bigger ideals other than the entire ring, that's going to show us that S hat has to be the entire ring R. And if S hat is the entire ring R, that's going to give us some nice properties that will eventually allow us to find a multiplicative inverse for little a plus S. So that's where we're going with this proof. So let S hat be this thing. Then I claim S hat is an ideal in R. Why is S hat an ideal in R? How do we know this thing, first of all, forms a subring and that it absorbs multiplication? The reason why we know that is because I said so, and you should never doubt me. I'm going to leave this as an exercise. This proof's already kind of a long one, and I don't want to muddle it up with proving S hat's an ideal. Be a fun little exercise for you to test how well you know how to prove things are ideals. So S hat is an ideal, and given any little s in S, big S, we can write little s as being equal to a times 0 plus little s, meaning little s has to be an element in S hat, because it can be written in the form a times something from our ring, this is the 0 element, plus little s. And then that tells us any element in big S has to be an element in big S hat. So big S is a subset of big S hat. So we know big S is a subset of big S hat. We also can show they're not equal. However, we can say that A is equal to a times 1 plus 0. And since 1 has to be an element in our ring, we assume our ring R has a multiplicative identity 1 to start with. 0 has to be an element in our ideal S. Why do we know 0 is an S? Well, we know 0 is an S because S is an ideal, which means it's a subring, which means it's a subgroup of R under addition, and thus any ideal has to always contain the additive identity from our ring. So it has to contain 0. So we can write A in the form A times something in our ring plus something in S, which tells us that A has to be an element in S hat. So we know A is in this set here, S hat that we defined. But we also know A is not an element in S. Because that's kind of one of our initial assumptions. We assumed A is not an element in S because we wanted A plus S to be the non-zero element in our quotient ring R mod S. Thus, what's that telling us? Well, that's going to tell us S is properly contained in S hat. That S hat is an ideal in our ring that contains everything S does and then some. This tells us right here, S hat contains everything S does, but we also know S hat contains at least one element that S does not, namely the element little a. So S is properly contained in S hat. And now we can use the fact that big S is maximal to say, hey, we have a maximal ideal. How is it possible that we have another ideal in our ring that is bigger than S, if S is maximal? Well, if S is maximal, the only possible way this can occur, that S is properly contained in some S hat, is if that S hat was the entire ring. Thus, since S is maximal in R, maximal in R, we know S hat has to be the entire ring. It's from the fact that there's no way to form a bigger ideal than a maximal ideal except to take the entire ring. So what does that mean? Well, if big S hat is the entire ring, big S hat has to contain every element within the ring R, including 1, the multiplicative identity. Because that's something in the ring, and if our ring is equal to this ideal S hat, then S hat has to contain it. So where are we? So what does it mean for 1 to be an S hat? Well, by definition, that's going to tell us that 1 is going to be equal to AR plus little s for some little r in big R and some little s in big S. And that's just by definition. 1 being in big S hat tells us 1 has to be able to be written in this form. So 1 is equal to AR plus little ar plus s. Well, that's then going to tell us that if we were to take the ideal 1 plus s, that's going to be the same as taking little ar plus s plus big S, because 1 and this thing are the same element. What do we know about this coset? Little ar plus little s plus s. It's going to give us some element in the quotient ring R mod s. Well, I claim this is the same as little ar plus big S. So what is that? Well, this right here is the set of all elements of the form little ar plus little s plus something in the ideal s. That's going to be the same as little ar plus s plus something in s. Because if we were to take little s specifically plus something in big S, that's just the same as taking something in big S to begin with, since little s is in big S. If you prefer, you could write this as little ar plus s plus little s plus big S, which is the same as little ar plus big S plus big S, and little ar plus s plus big S. Remember, big S is the 0 element, the additive identity in R mod S. Therefore, adding the ideal big S here changes nothing. So that's still going to give us little ar plus big S, which is the same as taking little a plus s times little r plus s. Oh my gosh, Dr. Gerstle, when is this part going to end? We're just about done with this part. Because look what we've proven. We've shown that little a plus big S times this little r plus big S is equal to 1 plus big S, because that's what was at the start of this string of equalities. Hence, little a plus big S has a multiplicative inverse. We found something we can multiply little a plus s by to get us to 1 plus s, namely this little r plus s. So this arbitrary non-zero element in R mod s has to have had a multiplicative inverse. That, combined with the fact that R mod s has a multiplicative identity and it has commutativity, that's enough to then tell us R mod s must be a field. And there we have it. What's that? What's that, Phil? You're saying we're not done? We still have to prove the backwards direction? Oh, good grief. All right, let's prove the backwards direction. So we showed that if S is maximal, then R mod S has to be a field. Now we need to go the opposite way and show if R mod S is a field, then S has to be maximal. Which fortunately, is a little bit short. So let's do that. So, backwards direction. So we're going to suppose that R mod S is a field, and our goal is going to be to show S is maximal, yeah? So we're going to suppose that big S hat is some ideal in R, not necessarily the same S hat from the forward direction, but it's some ideal in R such that big S is properly contained in big S hat. So we're going to suppose that we have some ideal S hat that properly contains our ideal big S. So if we want to show S has to be maximal, what do we need to prove? Well, in order to prove that big S is maximal, that it has no bigger ideals, we would need to show that if we can find an ideal S hat that's bigger than S, there's only one way that that should be possible, and that's that big S hat has to be the entire ring. If we can show that the only way to take an ideal strictly bigger than S, and the only way to show that S is maximal is to show if we take something strictly bigger than S, then that strictly bigger thing could only be the entire ring. So let's try and prove that. S is probably contained in S hat. So first of all, I'm going to let A be an element in S hat. And we're going to choose A specifically such that A is not an element in S. We should be able to do that. We assume that S hat properly contains S, meaning it contains everything S does, and then some. That means we should be able to choose some element that is in S hat but not in S, which I'm going to call A. And then, since A is not an element in S, that's going to tell us that if we were to take A hat plus S, or why do I call it A hat? Already enough hats in this proof already. Playing a video game right now, Stardew Valley, where my character's racking up a lot of hats, bringing some of them into this class, but I shouldn't bring unnecessary ones. So we know A plus S is not equal to S, since A itself was not an element in S. Hence, A plus S is non-zero in the ring R mod S, because the zero element in this ring is just S. So what does that tell us? Well, we assumed R mod S is a field, so if little a plus S is non-zero in R mod S, that means it should have a multiplicative inverse. So hence A plus S is non-zero in R mod S. So A plus S has a multiplicative inverse. I'll call it some little b plus S for some element b in our ring R. Because in field, by definition, in a field, every non-zero element has to have a multiplicative inverse. Well, if b plus s is a multiplicative inverse to a plus s, that means it should be the case that if we were to take 1 plus s, we would get a plus s times b plus s by definition, because multiplicative inverse is whatever you need to multiply by to get the multiplicative identity, which in this case is 1 plus s. So 1 plus s should be equal to a plus s times b plus s, which in turn is the same thing as ab plus s, which is going to then tell us if 1 plus s and ab plus s give us the same coset, the only way that happens is if 1 minus ab is an element in S. So right away we know that 1 minus ab is an element in S, but since S is properly contained in S hat, meaning everything in S is in S hat, that's also then going to tell us 1 minus ab is an element in S hat as well, because everything in S, including 1 minus ab, has to be an element in S hat. So where are we going with this? Our goal is going to be to show, remember, that S hat has to be the entire ring. How can we show that an ideal is equal to the entire ring? Well, we have one way of showing it. We could show that an ideal is the entire ring if that ideal contains, say, the multiplicative identity, which we proved towards the front of this packet, in fact. Actually, at the very front. If we can show S hat contains 1, the multiplicative identity in our ring R, by a theorem at the front of our packet, that immediately tells us S hat has to be the entire ring. So that's our goal now, is to show that 1 has to be an element in S hat. Almost there. So what are we showing? We're showing 1 minus little a times little b is an element in S hat. We can also say that since a is an element in S hat, that's something we assumed from the get-go, a is an element in S hat, and S hat is an ideal in our ring R. Thus, a times b has to also be an element in S hat. Why? Well, that's because by definition of an ideal, if you take something in the ideal times something in the larger ring, you still always have to end up back inside the ideal. That's the property that separates an ideal from just an ordinary subring. So since A is in the ideal and B is something in the ring, AB has to be in the ideal. So AB is an element in S hat. But what's this? AB is in S hat. 1 minus AB is in S hat. So since 1 minus AB and AB themselves are elements in S hat, since S hat automatically is an ideal, meaning it has to be a subring, meaning it's closed under addition, we can say since 1 minus AB is in S hat, and since AB is in S hat, thus their sum, which is just 1, is going to be in S hat, therefore S hat is the entire ring, therefore S hat to have been maximal, and life is hunky-dory. So let's write some of that down. And S hat is closed under addition as an ideal. This S hat has all of these things. 1 minus AB plus AB, which is the same as 1, has to be an element in S hat. Thing in S hat plus thing in S hat has to be in S hat. And then since 1 is in S hat, S hat has to be the entire ring. And thus, S is maximal. Since we just showed that if S is properly contained and S hat is contained in R, that we just showed that it had to have been the case that S hat is the entire ring. The only way to get a bigger ideal than S hat is to get the entire ring. My phone just buzzed like 10 times in the middle of that last sentence, and I'm wondering who's trying to text me so badly. So there's our theorem. We've shown in part 2 that if R mod S is a field, then S has to be maximal, and vice versa. If S is maximal, then R mod S had to have been a field. And similarly, if S is prime, then R mod S is an integral domain, and if R mod S is an integral domain, then S has to be prime. So let's end today's video. I know today's been a bit of a long one. We're almost there. I want to do one quick corollary to this theorem. And unlike this part right here, which I lied to you and said it was quick, this one actually will be quick. You can trust me. Wait. So here is our corollary. Corollary is going to say that if R is commutative ring with multiplicative identity. Is a commutative ring with multiplicative identity. And S is an ideal in R. Then then we can say if S is prime, or if S is maximal, then S must be prime. In other words, in a commutative ring with identity, all maximal ideals have to be prime. So let's prove this. This one's actually a really quick proof. And it's kind of a fun proof. I like this one. So here's our proof. Well, our proof is going to be this. S is maximal. According to our previous theorem, if S is maximal, that then is going to imply that R mod S is a field. By what we just proved. But if R mod S is a field, that's going to imply R mod S is an integral domain. Why is that? Well, that's something we actually proved at the end of the last packet, that all fields have to be integral domains. So in particular, if R mod S is a field, then R mod S has to be an integral domain. Which in turn, by again, the theorem we just proved is going to tell us that since R mod S is an integral domain, S is prime. And that's it. That's the whole proof. S is maximal, then the quotient ring's a field, which means the quotient ring's an integral domain, which means S is prime. And notice this doesn't work in reverse, because while all fields have to be integral domains, not all integral domains have to be fields. Also, by the way, this is going to tell us as a corollary that if P is prime, Z mod PZ, let's not say that. We'll say PZ is maximal in the ring of integers. Because since P, or blah, 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 blah. What am I saying? Ignore this corollary. This is what happens when I try to make stuff up on the spot. You already knew that. So, just as a quick last note, not made up stuff that's actually not falling as a corollary to what we just said, let's talk about why the vice versa is not necessarily true. We said all maximal ideals must be prime, but not vice versa. We saw an example early on in the packet where this was not the case, but just to revisit it from a different perspective, answer is no. And here's an example. We know if we were to take the ring of integer polynomials and mod out by the ideal generated by x, I'm going to leave this to you as an exercise. Prove this is isomorphic to the integers for me. Hint, first isomorphism theorem. And we know the integers, the ring of integers is an integral domain, but not a field. Which in turn is going to tell us that this lovely thing, that the quotient ring, integer polynomials mod out by ideal generated by x, is an integral domain, but not a field. And finally, that in turn is going to tell us that the ideal generated by x is prime in the ring of all integer polynomials, but not maximal. We know this ideal has to be prime because when we mod out by it, we get an integral domain. But we also know it's not maximal because when we mod out by this ideal, we do not get a field. That's kind of another kind of quick and easier way to actually show this ideal is prime but not maximal. All right, that's going to do it for today. One more packet to go. We're going to talk about the difference between prime and irreducible elements in a ring and why all of your high school and grade school teachers lied to you about what prime numbers are. That's going to do it for the semester. Hope you're all still staying safe and healthy. See y'all